This is question 2 from June 2009, and it's from module 4, and it's a gas laws question, and specifically on Boyle's law. So a student has said that the volume V of air is proportional to the pressure P applied, and we're told there are 3 important omissions. Well, if we look at this, first of all, we can see Boyle's law states that the volume V is inversely proportional, so that's an omission, so it should read there, inversely proportional to the pressure applied, and then it's for a fixed mass of gas, the volume V of air is inversely proportional to the pressure applied at a constant temperature. So we've got for a fixed mass, constant temperature, and inversely proportional. So the first omission then is that it's omitted fixed mass of gas has been omitted. And why is that? Well, it's because Boyle's law is true only for a fixed mass where the number of molecules stays constant. Okay, so we must have the same number of molecules in order for Boyle's law to be true. Omission 2 then, that was for a constant temperature, has to apply. So we need a constant temperature to go into that somewhere. The explanation of that then, well, any change in temperature will cause a change in pressure or volume. So in order for us to see the relationship in Boyle's law, we need to have a constant temperature. Omission 3 then, that was inversely proportional, was omitted. So it said proportional rather than inversely proportional, and the explanation for that is that as the pressure increases, the volume decreases. So the relationship is an inverse relationship rather than a directly proportional relationship as stated. We then have a calculation question. So we have, on a day when the atmospheric pressure is 102 kilopascals, the outside temperature is 12, the pressure in a car tire is 175 above atmospheric pressure. This 175 above, we need to add it on to the 102, so that's going to be important to do that. After a long journey, the temperature of the air in the tire rises, and again 28 degrees Celsius, 12 degrees Celsius, we need to change those to Kelvin. So calculate the pressure above atmospheric of the air in the tire at 28, assume that the volume of the tire remains constant. So volume remains constant, so we can say P1 over T1 equals P2 over T2. So that's the calculation that we're going to do, and so we can simply say, well, the first pressure is 277, that's 102, 102 plus 175, so that gives us 277 over, and that's going to be a pressure of 277 over a temperature of 12, which is 285. Okay, so we have 285 Kelvin is equal to the new pressure that we're looking at 28, which will be 301. Therefore, that means that the pressure that we're looking for is equal to 301 times 277 divided by 285, which is equal to, and then we look at that, that's going to be equal to 292.6. So it's 292.6. Sorry, I've written that incorrectly. 292.6, and then we have to subtract 175 from that, and that gives us 190.6 kilopascals. So 190.6, and that's important, just that one at the end, that we have to subtract the 175 again from that. So we just said P1 over T1 equal P2 over T2. Pressure was 277, temperature was 285, new pressure we're looking for 301. Rearrange that, so P2 is equal to 301 times 277 over 285, which gives us the 292.6, but we need to subtract the 175 in order to get 190.6. And then the very last part of the question is applying it to racing car tires. Nitrogen commonly replaces air because the temperature of the tire changes can be more accurately predicted. So how can we do what? Suggest how this information can be used by a racing team. Well, obviously then they can have the optimal tire pressure can be established for best road grip or correct height of car above the ground. And again, that's just to give the downward force, the G force acting on it.